Welcome back, dear students, to my lecture 3 on numerical solution of differential equations. So, we have seen that Euler's method is less efficient in practical problems because if h is not sufficiently small, then this method gives inaccurate result. So, Runge-Kutta type methods, which include Euler and modified Euler as special cases, are called single step methods, because they use only the information from the last step computed. In this, they have the ability to perform the next step with a different step size and are ideal for beginning the solution where only the initial conditions are available. After the solution has begun, however, there is additional information available about the function and its derivatives, obviously. If you are wise enough to retain it in the memory of the computer, a multi-step method is one that takes advantage of this fact. So the advantages of the Euler's method have been modified in Runge-Kutta method. So single step methods for solving dy dx equal to fxy. If I write dy dx, the initial value problem is dy dx equal to function of xy and at some initial conditions, require only a knowledge of the numerical solution yi in order to compute the next value yi plus 1. This has obvious advantages over the p-step multi-step methods that usually several past values yi plus 1, etc. Since then, the additional initial values y1, etc., yp minus 1 have to be computed by some other numerical methods. Now, you have seen this is the Taylor series expansion. The general single step method for order p may be obtained by expanding x plus h, yx plus h by Taylor's theorem, as this is the Taylor series expansion, and we have a lot of talking we have discussed about this Taylor series. However, the derivatives are still likely to be quite time consuming to evaluate, and it appears that methods based on evaluating just fxy will remain more efficient. To imitate the Taylor series method while evaluating only fxy, we turn to the Runge-Kutta formulas. Actually, Runge and Kutta are two German mathematicians, and the simple Euler method comes from using just one term from the Taylor series for y equal to x, yx expanded about x equal to x naught, the initial point. The modified Euler method can be derived from using two terms, y of y of x naught plus h. You can write by Taylor series expansion y x naught plus h if y dashed x naught plus h square by factorial to y double dashed x naught. If we replace the second derivative with a backward difference approximation, so this is the second derivative. If you replace the second derivative by the backward difference approximation, then it comes to be like this. This is the result. That it is replaced by h square by factorial 2 y prime x naught plus y prime denotes the first derivative, first order derivative, minus y prime x naught by h. So if you simplify, you will get y of x naught plus h equal to y x naught plus h y x naught y prime x naught plus h plus y prime x naught by 2. We get the formula for the modified method. This is the formula for the modified method. So what if we use more terms of the Taylor series? This is only the up to the second order expansion. Higher order terms are neglected, that is third order, fourth order terms are neglected. This is only up to second order. So what will be the effect if we use more terms of the Taylor series? So two German, that I was talking about, two German mathematicians, Runge and Kutta, developed algorithms for using more than two terms of the series. So they have developed the algorithm for using more than two terms. We will consider only fourth and fifth order formulas. The modified Euler method is a second order Runge-Kutta method. So modified Euler is nothing but the second order. Actually, modified Euler is a special case of the Runge-Kutta, second order Runge-Kutta method that we'll see actually. So that is the introduction of this lecture today, that we are talking about Runge-Kutta's method, Runge-Kutta's second order method and fourth order method. Let's come to the process. So second order Runge-Kutta method are obtained by using a weighted average of two increments to yx naught, k1 and k2. Actually k1 and k2 are two increments, weighted average of two increments to yx naught for the equation, this one dy dx equal to fxy. So what is the iteration formula? The iteration formula is given by this: yn plus 1 equal to yn plus ak1 plus bk2, and where k1 is given by h f of xn comma yn, k2 is given by h, k2 is equal to h f of xn plus alpha h comma yn plus beta k1. So you are substituting k1 from here. Okay, this is k1. You are getting the k1 from the previous value. You have to calculate like this, and this is the modified value of y, and k2 is given by this. And ultimately, if you have k1, if you have k2, you can get yn plus 1. So this is the second order Runge-Kutta method. Okay. Now some derivations from the second order Runge-Kutta method. Now we can think of the values k1, k2 as estimates of the change in y and x, change in y when x advances by h, because they are the product of the change in x and a value for the slope of the curve dy dx. So the Runge-Kutta methods always use the simple Euler estimate, simple Euler, as the first estimate of delta y. The other estimate is taken with x and y stepped up by the fractions alpha and beta of h, and the earlier estimate of delta y, k1. So our problem is to devise a scheme of choosing the four parameters a, b, alpha, beta. So you have four parameters a, b, alpha and beta. Look at that. A is a parameter in the first line, b is a parameter, last line alpha and beta are the parameters. So the four parameters you have to choose. That is the target. Now special cases. For dy dx equal to y fxy, we have this Taylor series expansion yn plus 1 equal to yn plus h fxn yn h square by factorial to f double prime, that is the double derivative fxn yn, etc. An equivalent form, because you know this relation df dx, you can write fx partial derivative with respect to x plus partial derivative with respect to y dy dx, that is the df dx. So if you replace this value, then it will be in the form, the equivalent form 2 is the equivalent form. So in this case, this is for all the derivatives in equation 2 are called at the point xn yn, are calculated at the point xn yn. Now we write equation 2 by substituting the definitions of k1 and k2. So what is the definitions of k1 and k2? It's given in the Runge-Kutta second order method. Look at that. This is k1 and this is k2. So you replace k1 and k2. So you have equation 2 can be written as, okay, in terms of ah fxn yn plus bh f xn plus alpha h yn plus beta h fxn yn. So that is using, you are rewriting equation 2, this equation. Okay, and to make the last term of equation 3, this is the last term, to make the last term of equation 3 comparable to equation 2, we expand fxy in Taylor series in terms of x and yn. You have to expand fxy in terms of xn yn, in terms of Taylor series of x and yn, remembering that f is a function of two variables, retaining only first derivative term. So you have to expand up to first derivative. So this can be the last term of equation 3 can be written as this one, f plus fx, that is partial derivative with respect to x, alpha h, plus f partial derivative with respect to y, beta h fn. Substituting from equation 4 into equation 3, we have yn plus 1 equal to yn, ah fn plus bh, this one. You are substituting in equation 3 actually, this replacing. So you are using 4 and you are arrive at that. Now this, on rearranging, you will have number 5, equation number 5. Now equation 5 will be identical to equation 2. What is equation 2? Let's go to, this is your equation 2, and you are rearranging, what you get is equation 5. Now you compare these two. Look at 2. 2 is h fx n yn, h squared half fx, that is partial derivative with respect to x, plus half fy partial derivative with respect to y, f. And your 5 is this one. So a plus b equal to 1, okay, and alpha b equal to half and beta b equal to half. That is by equation 2. Equation 5 will be identical to equation 2 if this. So these are the relations between the parameters. A plus b equal to half, 1, alpha beta equal to half, alpha b equal to half and beta b equal to half. That is you are comparing. So these are the deductions. Now look at that. There are some values. Note that only 3 equations need to be satisfied by the 4 unknowns. We can choose one value arbitrarily with minor restrictions. Hence, we have a set of second order methods. One choice can be a equal to 0, b equal to 1, alpha equal to half, beta equal to half. This gives the midpoint method. Okay, clear? We talked about the midpoint method in the last video. Another choice can be a equal to half, b equal to half, alpha equal to 1, beta equal to 1, which gives the modified Euler method. So look at that. Midpoint method and Euler method, modified method, is a special case of the Runge-Kutta second order. Okay, so these are the special cases of second order Runge-Kutta methods. So these are the derivations. This is the important derivations. So you have to go through the steps. This is quite easy to handle. Now, what is the fourth order Runge-Kutta methods? So fourth order Runge-Kutta methods are most widely used and are derived in similar fashion. Greater complexity results from having to compare terms through h to the power 4, order of h to the power 4, and this gives a set of 11 equations and 13 unknowns. I'm just giving you the brief history of fourth order Runge-Kutta methods. So I'm not showing the derivations and all that. That is not required in this lecture. The set of 11 equations can be solved with 2 unknowns being chosen arbitrarily. The most commonly used set of values leads to the procedure. What is the procedure? These are the set of RK4, Runge-Kutta method of order 4. So yn plus 1, look at that k1. K1 is same, but k2 is a little bit modified, xn plus h by 2, yn plus k1 by 2. So you are at the previous step, you have calculated k1. So you are using k1 here. Again, you have calculated k2. So you will use k2 here in the next step, that is for k3. K3 is xn plus h by 2, h times f of xn plus h by 2, yn plus k2 by 2. And lastly, you are using k4 in k3 in k4. So that will be xn plus h plus yn plus k3. So that's the use of k1, k2, k3, k4. Okay. And finally, you will get yn plus 1 equal to yn plus 1/6 of k1 plus 2k2 plus 2k3 plus k4. So you are taking some weighted average. These are called weighted average. So Runge-Kutta method actually taken some weighted mean to calculate the slope and all that. So this is about Runge-Kutta second order and fourth order. And fourth order is widely used, very important method for finding differential equation, solution of the differential equation. Now let's come to the last part. What are the advantages? The best known one-step methods are the Runge-Kutta methods. Best known one-step methods. They are fairly simple to program. You can easily program the method, and their truncation error can be controlled in a more straightforward manner than for the multi-step methods. So that is the big advantage of the Runge-Kutta methods. Also, it requires only the value of the function at some selected points on the subinterval, and it is stable. For the fixed order multi-step methods that were used more commonly in the past, the Runge-Kutta methods were the usual tool for calculating the needed initial values for the multi-step methods. Another favorable aspect of Runge-Kutta method is that it has a simple form and reasonably good accuracy, but it is computationally more laborious than the multi-step methods to be discussed in later chapters. However, the Runge-Kutta methods may be used for starting the solution for such multi-step methods. So for multi-step method, you can use the Runge-Kutta method for starting the solution. So these are the big advantages of Runge-Kutta methods. Obviously, there are some disadvantages. So what are the disadvantages? An important drawback of the Runge-Kutta method is that there is no suitable means of checking the computation or estimating the error at any step. No, nothing is there. No suitable means. If an error in computation creeps in at any stage, then it is propagated undetected through the subsequent steps. The major disadvantage of Runge-Kutta method is that they use many more evaluations of the derivative fxy to attain the same accuracy as compared with the multi-step methods. So what you see, multi-step methods are the more modern methods, and throughout the globe it is accepted as the methods for finding the ordinary differential. But that is not in our scope. That is not in the scope of our syllabus. So that's all for today, and that is our solving uh, differential equations, numerical solution of differential equations. That's complete in 3 lecture up to Runge-Kutta method. So thank you all of you. Subscribe my channel and share my videos with your friends, students, guides, mentors. Thank you all of you. Take care.